discovered that there was Oh yeah, so there is the notification about the recording. Okay, so basically, we discovered that there was a lot to cover, even in the context of continuous time systems and even for linear time invariant systems. So we started from this topic here with a focus in mind on finding state space approaches that could be later extended to more general scenario. So let's start with the idea of data-driven control. So here in this slide, I present some images which are pretty much unconventional examples of control applications. Let's say usually someone may think about robotics, for instance, as the very first goal for control applications, but these probably are more challenging situations where data-driven control can have a lot to say because, of course, anytime a model, an accurate model of a system is available, it's a better strategy overall. But there are some situations like those presented here, like smart buildings, renewable energies, neuromorphic electronics, or smart actuators that can be seen here. Usually, the devices that need to be controlled are very different between one and another. There are many copies of them, and they come in all different sizes and shapes. And the dynamics have very difficult fundamental physical laws and they change over time. So in these applications, there is a very clear advantage, both from a time and economic point of view, of moving towards something which is more data-based. But anyway, data-driven control is a term that is not new at all. I mean, actually, the term data-driven is probably fashionable right now, but it has a very old story. In fact, even in 1942, the method of Ziegler and Nichols of tuning PID controllers was, by all means, what we intend right now as a data-driven direct approach. But of course, in the 60s and the 70s, the approaches of system identification and adaptive control were clear attempts and very successful ones in using data to learn both models and controllers. And more recently, actually not so recently, reinforcement learning has become a very successful paradigm in this context. More recently, actually with a delay of 15 years from the original paper, there has been this trend based on the use of the Willems et al. Fundamental lemma. Which was originally published in 2005, but only in 2019, the first real burst of results came from that context. And first of all, people started saying, well, since this lemma is particularly useful for describing models using directly data, they said, how about doing MPC? So to predict the behavior and put that thing inside an optimization algorithm in MPC. And so the so-called data-enabled predictive control was born. And just a year after that, people started also using similar ideas to develop directly LMIs or other optimization techniques in order to obtain a controller directly from data. And this in particular is the focus of this seminar. So just to give an idea of what I'm talking about, let's consider for simplicity, and I know that the topic will then shift to continuous time systems, but it's much easier to understand that from discrete time systems. So let's consider a very simple linear time invariant system formulated in discrete time. So this plus here is used to indicate the discrete time updates. So suppose that this system is completely unknown, but we have available an input and state trajectory from it. And note that we need an additional sample for the state. And the reason is that we can use these samples to generate some batches, which are in particular the collection of all inputs. and then two different sets of state batches, which have a one time step shift. Let's assume for now, which is a very reasonable thing, especially if someone thinks about system identification, that the stack of the input and state with the minus sign here has this matrix has full rank. And why this is reasonable from a system identification perspective is that using that we can obtain actually an open loop representation of the plant. This result here, which is slightly more general than the classical system identification result, is of course based on that and has here a general right inverse of this matrix. This result here is directly connected to Willem's lemma, which says that basically when you have full rank of this matrix, any input and state vector, actually the actual Willem's lemma is formulated in the context of having input-output data, but this is a simplified scenario which works the same way basically. So any input and state vector can be represented as a linear combination of this matrix here. But this is nothing else than, mathematically speaking, a consequence of the Ruche-Capelli theorem. And this is the mathematical tool that is used in the LMI-based framework to derive some methods to find controller directly from data. So why did I stress open loop representation? The reason is that we can also, and I'm going to show just in a couple of seconds, we can also obtain a closed loop representation of the system. What do I mean by that? Well, let's go back, well, to our formulation. So we have our discrete time system, we have our data batches, and let's now consider, in addition to that, some static feedback law of the form u equal to k times x. So this feedback law has a very generic gain k. So consider any one of them. It doesn't really matter if it stabilizes or not the system. Using that, we can do very simple computations. In particular, using the Ruche-Capelli theorem again, we can show that any matrix of this form, because ux minus has full rank, well, this matrix here can be represented again as a linear combination. Of course, this will be a matrix, this gk, instead of a vector, as before, but we can do the same thing. And of course, this comes from the way in which we collected the data and how they are related to the difference equation here. We have this relationship between x plus and u and x minus. So now let's suppose that we want to represent a plus bk. What we achieve is that a plus bk can be shown to be this product here. This is just an expansion of the product. And after that, ki can be replaced with the expression that was obtained here. But note that at this point, BA times UX minus is nothing else than this guy here. And so we obtain X plus. And we have finally obtained this very interesting conceptual result, that is that for any K that you may think of, using data, we can obtain the representation of a system in closed loop with that K. And so note in particular that this is equal to A plus BK, and this can be used for data-driven design. In fact, if one thinks about that, so this is a summary of what we have achieved so far, if we have that this is the closed loop behavior of our system, in order to perform data-driven control, the immediate idea is to, well, impose that this matrix is sure, so all its eigenvalues are in the unit disk. How can we impose that? Well, we require, of course, that there exists a symmetric and positive definite matrix P, which satisfies this Lyapunov inequality. Not in particular, this is just a slight modification to what could be like the expected expression that we use the transpose here, and it is necessary just for simplifications of the computations. Nothing really surprising. In fact, if this matrix here is sure, of course, also its transpose is. So this is not what we need yet, because we can do some modifications, in particular change of variables. Note that both gk and p are so far unknowns, and we replace gk times p with this unknown matrix q. And what we obtain by basically expanding here p with p minus 1 p, and let's remember also that p is a symmetric. So we obtain this expression. And this is much more useful because we can reformulate this together with p positive definite using the Schur complement. And in particular, we obtain this constraint here, which collects p positive definite and all this guy here negative definite. Let's now note that we have additional constraints because we have started all this story from this theorem which linked gk with k. And if we post multiply both items with p, we obtain kp equal to u gk times p, but let's remember that q is equal to gk times p, so we obtain this equation. And if you do the same thing with the second row, second block row, we obtain this equation here. So we have transformed basically the data batches that we have here above into constraints and relationships that express directly some specifications for stability of the closed loop system. So let's summarize this result. So if you have the data batches, you can just plug them inside this linear matrix inequality with the knowns P and Q. And if you can find a solution to this LMI, then the simplest thing that you can do is simply compute K by using the relationship in the that I showed before by just inverting P, and we have obtained a stabilizing gain. So let's summarize also formally this result, which is that, well, first of all, if the rank condition here holds, the LMI is feasible. So we have a guarantee that there exists a solution to that LMI. And note that this is just a sufficient condition. It is not necessary. And this is an interesting thing because it means that even if this rank condition doesn't hold, there are situations where feasibility of the LMI is guaranteed. Another part of this result is that any solution of the LMI, regardless of the rank condition shown here, is such that A plus BK is sure. So, given this result, which is basically somehow the direct version of batch identification plus stabilization, we may think, what is the connection between this direct approach and the indirect approaches, which are historically very well documented? Well, so given a data set, we have these two basically parallel tool chains that we can implement. The direct approach is the one that I expressed just before. So you solve an LMI and you plug the solution of the LMI into the computation of a gain here. So we have seen that feasibility of this LMI is guaranteed as a sufficient condition, from the sufficient condition, which is that the rank of ux minus is full. On the other hand, if you think about the indirect approach, and considering here just the simplest way to perform indirect design, what you do is you solve an optimization problem, which is a least squares problem, where you find estimates of B and A, and then you plug them in any model-based approach that you may think of, even another LMI. And it is known that instead, in this context, in order to achieve the identification of B and A, this condition is not just sufficient, but also necessary. So in some way, slightly, of course, we already see that even if there is no noise in the two scenarios, in some way the direct approach gives a little bit more. And in the noisy situation, there are other advantages which can be basically summarized as this philosophical sentence that the best predictor is not necessarily the best model also for control, given some noises that generate a set of potential systems. So, in the noise-free scenario, a very interesting read is given by this seminal paper on data informativity, where this thing about the less information needed in direct approaches is fully explained. It is also interesting to notice that there is a specific application where the two worlds are actually coincident, which is LQR. So if you, instead of just solving a stability problem, but you also add some optimization criteria, well, in that case, it turns out that if you solve that using a direct approach or an indirect approach, the two solutions are exactly the same and they require the exact same assumptions, which is somehow interesting. Um, so at this point, one may ask, what about continuous time systems? Of course, the main goal of this presentation is about continuous time systems. Well, in that case, one may just say, well, let's do the same exact thing in some slightly different flavor, of course, because now what we need in order to recover the exact same approach is to use not anymore the shifted values of the state, but the derivatives of the state. So in this case, if we assume, and this I recognize is a very strong assumption, if we assume that we can measure this matrix X dot, then we can plug these batches in an LMI, which is very similar, even simpler than the one before, because in this case, to require that the closed loop matrix is Horvitz is simpler. We don't need the Schur complement. And so we obtain something which is absolutely parallel to what we have achieved before. So we have that feasibility is guaranteed by this rank condition. And furthermore, for any solution, regardless of the rank condition, A plus BK is Horvitz. But there is a huge caveat in this context, which was not present in the discrete time context, which is that we need X dot. And this is a huge problem because both mathematically speaking and from an engineering perspective, it's a problem. Well, mathematically speaking, we know that ODEs hold almost everywhere. So there may even happen situations where the derivative of the state doesn't even exist. So we cannot sample it. From an engineering perspective, instead, the main problem is that we need to work with noisy data. And what happens when we have noise? We cannot reliably compute directly a derivative. There will be a disturbance to add, but is it reasonable to do so? Well, in most scenarios, unfortunately, it's really hard to have some reliable computation of the derivative. And if we look at the more general and more realistic scenario where we have just an output measurement, so we don't have full access to the state, well, the derivative situation is even worse because we would need multiple derivatives of both the input and the output of the data that we have acquired. So here in this presentation, I also add another question that is, okay, so let's suppose that we can aim and we can solve at stabilization, but what about even going further towards reference tracking and disturbance rejection? Like if the system that you acquire the data is perturbed by some exogenous signal. So it turns out that in order to address in a formal and complete way all these problems, a very nice setting, well established in the literature, is that of output regulation. So just to summarize, for being on the same, like having a common background on this, the output regulation problem, which can be found with a nice explanation in this book here, tries to solve three problems all at once. So first of all, to achieve stabilization of a system. Secondly, to reject potentially external disturbance that may affect the system, and also ensure tracking of some regulated output. Uh, so instead of having a system as before, now we can consider a system which is affected by the signal W here with matrices P and Q. And W in general may be any signal, of course. But if we want to solve all the problems said in this list here in general, it's a really formidable problem. So what is done usually in the literature of output regulation is to assume that W is not available, which would be a too strong assumption, but we know a model of it. So we know how it behaves, the class of signals that will appear in the system. And in particular, in the linear case, the usual thing that people do is to consider the so-called exosystem, which is basically a model for all types of signals that we admit to be perturbing our plant. And the assumption, which is not necessary, but is usually given for making the problem interesting in some way, is to say that S is neutrally stable, which means that all eigenvalues are semi-simple and on the imaginary axis. In other words, the minimal polynomial of S has all simple roots on the imaginary axis. And in particular, in our framework, we need S to be known. So this is just a hint to a potential future work derived from this approach here. So why do we exclude stable or unstable, I mean, asymptotically stable or unstable exosystems? Well, because if the exosystem contains stable modes, they are uninteresting, let's say. We can just solve a stabilization problem and those modes will vanish. Uh, about unstable modes, well, we just don't like them for being unstable, but all the theory developed here works also in that scenario. So there is no problem about that. So, in order to specify our regulation problem, because as said here, we need to specify some form of tracking objective. So we can divide Y into E, which is the so-called regulated output, and some additional residual outputs, which are used just for additional measurement from the plant in order to design a controller. So overall, informally speaking, what we want to achieve is to design a controller, of course, an output feedback controller for this plant affected by the exosystem so that all the signals in closed loop are bounded. And additionally, the regulated error converges asymptotically to zero. So to summarize, more formally right now, we have an unknown plant where in particular we can see here the regulated output. We have an exosystem. And now let's say what the assumptions are. So the assumption about the plant is that AB is controllable and CA is observable, so that the transfer matrix, actually the realization of the transfer matrix from the input to the output is minimal in this case. And Also, we need this assumption, this condition here, which is called non-resonance condition in the literature, which informally speaking means that all the transmission zeros of the plant from U to E do not coincide with the eigenvalues of the exosystem. So given these assumptions, the problem is that we have from the system acquired a data set of the form U of t, Y of t, and note that this data set is influenced by W when we acquire data. And after that, the objective formally is to design a dynamical system, this controller here, whose data, so AC, BC, CC, and DC, are designed just from U of t and Y of t, so that we obtain, first of all, closed loop stability of the interconnection when W is equal to 0. And furthermore, for any initial condition x, xi, and W, there is this limit condition for the regulated output. So, of course, there is a lot to process. So probably, and in fact, this is the thread, the stream of the presentation. Now we first focus on the problem of stabilization, and then we will add also the regulation part. And of course, we are in an output feedback scenario. So it's reasonable to think that in this context, we need to look at observer design in some way. We will embed in some way a concept related to observer design. And so this is the idea that allowed to remove any information of both state, so just to work with the output, and also to remove any need for derivatives, which is to look at the classical observer design techniques and view them in a different perspective in order to achieve data-driven control. So let's start just to provide some context to the very well-known by all of us technique for observer design in a model-based setting. So for simplicity, let's not even consider the presence of an input because it's not necessary here to understand the framework, but we just have an observable pair. So what we do usually is to, by the way, I notice now that we have an input in the observer, but yeah, let's forget about this. The usual approach to design an observer for this model here is to just copy the dynamics and then add some some output injection term, which ensures, using the matrix gain L, that A minus LC is orbit, so that we have this error dynamics, which allows us to recover asymptotically the value of X. But if one looks at the literature, and in particular the original paper by Leuenberger, his idea was slightly different. And yeah, of course, he provided also this approach, but his tool chain to achieve that was slightly different. And in particular, his idea was to consider actually a change of coordinates. What change of coordinates? Well, a change of coordinates, this z equal to t times x, where the system in the transformed coordinates has a nice and useful structure for reconstruction. In particular, what he proposed was to obtain a change of coordinates where we have then that the state matrix is Hurwitz. But in particular, notice that in these coordinates, there is also an output injection term here. So here is how the original model is recovered somehow. But the very nice thing about moving into this direction is that then the observer design is trivial, because the only thing that we need to do once this lambda here is Hurwitz is just to copy the system. And in fact, if we design an observer which is given by this copy of the differential equation above, we obtain a very nice, constructive, even linear behavior. And we can also recover the original estimates by just applying the inverse of the transformation. So we can say that the by now standard approach for observer design involves not introducing this change of coordinates, so to remain in the original one with some special choices. But this approach here is the actual original idea proposed by Leuenberger. And one may ask, well, how do we compute t? The computation of t involves this matrix equation here, which is called Sylvester equation. Um, there are interesting considerations to do about the solvability of this matrix equation, but let's just say for now that in the single output case, it is known that if the pair that is chosen here is controllable, lambda is Hurwitz, and the spectra of A and lambda are disjoint, then the matrix T exists, is unique and invertible. This is a very simple scenario, but it gives an idea of the fact that it's solvable. But this is not all. This is just the original idea of Leuenberger. And why is it interesting? Well, because people in the past decades have worked in order to use this idea to move to the nonlinear context. When considering a nonlinear system, there is this interesting thing that we cannot any longer aim at a change of coordinates. It's not sufficient, usually. What we want to do is instead finding a map which is potentially not just transforming, so it's not necessarily a diffeomorphism. It can also be something that puts the system from the original representation into a higher dimensional system. So we're in some way, generally, lifting the system to a higher dimensional dynamics. And the nice thing is that under some assumptions, it's possible to do the same exact thing as before. So we can find a transformation that allows to lift the system into a structure that can be trivially used for observer design. And this idea is basically this. You start from a smaller dimensional system and you move to a higher dimensional system where, hopefully, the dynamics is easier. Note that also other approaches in the recent literature do something similar. If you think, for instance, about the Koopman operator theory, you lift your trajectories in order to simplify your approach for whatever, control, estimation, anything. So in this case, it's interesting to notice that we can simply copy the dynamics, and then using this copy, we will obtain an estimate in the lifted coordinates. And the previous Sylvester equation now becomes a differential equation. Of course, there are some caveats. The first one is, can we go back from the estimate of z to the estimate of x hat? Well, not always. And even at a more fundamental level, do we have the existence, the guarantee of an existence of of this differential equation? Well, these are questions that have been successfully addressed in the context of linear time invariant, of nonlinear time invariant systems, also for nonlinear time varying systems, but not fully for systems with inputs. Because anytime there is an input that is transformed into an explicit dependence on time in the first in the differential equation and then in the partial differential equation. So apart from these considerations for nonlinear Leuenberger observers, one may think, well, what could be done in a similar way in our situation? Can we lift our trajectories in order to obtain a simpler representation that we can use then for data-driven design? It turns out that the answer is positive, and it's grounded on classical adaptive observer design, and it's here presented in a state space context. So the interesting aspect is the state space interpretation of the classical approaches of adaptive observer design. So let's start from a controllable and observable system without any perturbation, and for now. And let's consider the ideas before with a very slight twist. So our idea is to consider also a lifted system, which has very similar properties as before. And in particular, these F, G, and L need to be fully user defined, where all the uncertainties will just be in H. And notice that now we are not considering a transformation from the original system to the new one, but vice versa. So instead of looking for an immersion, which was what was done in the context of nonlinear Lemberger observers, what is done here is to find a submersion. And in particular, it turns out that we can give a very general definition of all systems that work for data-driven control. So if we rewrite basically y here as hz, we obtain this system. And from this system, we can also express a matrix equation in H and an additional unknown matrix pi, unknown because we don't know the matrices of the system. And this matrix equation, set of matrix equations here, is what basically links the two worlds. And so pi here is exactly the submersion I was talking about before. So this class of systems is, of course, a non-minimal realization because these matrix equations here express the fact that the two systems are input-output equivalent. So in this context, they are rightfully to be called as like this is a non-minimal realization of the other. But it is also a canonical non-minimal realization using the literature, the nomenclature of output regulation, because in that context, usually the state matrix is expanded into a Horvitz matrix. And in fact, like in observer design theory, we need a Horvitz matrix in order to obtain some kind of contraction property. And then there is either feedback or output injection parameterization of the unknown parts, which is given here by this term here. So I just stress again that in order to obtain this realization, the important part is to have that F, G, and L, so the matrices of the differential equation, are fully user-defined, and so they are known. And all uncertainty is moved to the output map. This is really important to perform data-driven control. And you can find all the results related to this class of non-minimal realizations in this preprint that was sent like a month and a half ago. So let's see how we can use that non-minimal realization. Well, exactly as in observer design, and in fact, here we're somehow trying to revisit classical observer design control. So we can copy the non-minimal realization. We know we have full information on F, G, and L, so we can process the input and the output from the plant using this dynamics here. And once we obtain that, we can compute an estimation error. Of course, notice that in order to have this estimation error, we're just doing this for analysis because pi is not available for the designer. It's just used to show the properties for the analysis of the closed loop system. So using the realization equations shown in the previous slide, we can obtain this cascade dynamics here, where epsilon is the observer estimation error, and then this term epsilon is a perturbation to a system where we have this F plus LH, which is exactly the state matrix of the canonical non-minimum realization, and G is the input matrix of that. So it's pretty nice. What are the properties of this? Well, first of all, we have that F plus LHG is stabilizable. So it's very nice because now using that, if A minus pi LC, which is given here, is Hurwitz, then we have that the whole cascade is stabilizable. And so we obtain that in order to compute a controller for this overall cascade, we just need to find a static feedback law based on the available signals, z hat. And if you think about that, it's exactly the same thing that you do every time you design an observer, a Weinberger observer, and then you perform a static feedback law using the observer estimates. And this can be seen in particular by choosing pi equal to I. Of course, this cannot be done in the data-driven context, but if you assume just for a second that the plant matrices are known, you recover the classical theory. But now the big question, of course, is can we recover, can we find a stabilizing gain K using just the input-output data here? Well, it turns out that the answer is positive, and we can design basically a filter for the data, which is based on this observer dynamics. So let's see the equation right now. So we have, as said before, the input-output data set. And let's plug these signals here, which are available in a fixed interval. We plug them into a filter, which is just the simulation of the system, of the observer for that interval. What we obtain is exactly the same thing as shown before. And in particular, this differential equation holds, of course, almost everywhere, but over all the interval where we have our data set. Notice that we are not fully satisfied with this representation because epsilon is not available. It's not a known signal because it depends on the states of the plant and on unknown matrices. But we have a very interesting property that can be used basically to replace epsilon with something that we instead know. And the interesting thing is that every mode of this matrix here, which is Hurwitz, is a mode of F. So we are the people who assign the behavior, the evolution of epsilon in some alternative coordinates. So what we can do is to basically choose a reduced form of matrix F. In particular, we remove any redundant modes by choosing a matrix F0 whose characteristic polynomial coincides with the minimal polynomial of F. This is, I'll go very quick on this because it's not very conceptual. It's just a way to simplify the computations. Anyway, we choose also a vector G0, which is controllable with the with F0. And we have this very interesting result. That is that the term LC epsilon, so this cross term here, LC times epsilon of t, is equal for that interval of time to d chi of t, where chi of t is generated by a differential equation of this form here, with initial condition given by G0. So the very nice consequence of this lemma here is that we can replace in this differential equation epsilon with chi. But the difference is that chi is fully assigned. So we are those who choose the value of chi because we are simulating it. And so if you look at this differential equation with specific initial conditions here, we have obtained a fully known, from a signal perspective, representation of data which are not the original data, which are u and y, but they are related to them. And so we have a filter-based representation of the dynamics. The nice thing is that if you look back at what could be done if the derivatives were available, we are exactly in that point. Because now, using all these tools, we have obtained a representation where chi dot and z dot, z hat dot, are fully available. And so we can use that technique as before. I will go very quick on this because it's just a consequence of the previous results. Um, Basically, once you have this differential equation, you can collect a data set of this form. And once you have the data set, you can use the same arguments of having full rank of some data matrices, and using the Rusche-Capelli theorem, we can find, after some computations, that your data allow to define a closed loop matrix for the system on which we can impose an LMI to obtain that there is closed loop stability. So in particular, now I will present the first result of this presentation, which is the algorithm that allows to obtain stabilization, not regulation so far. So for stabilization, using data-driven techniques, you basically, just to summarize, start with an input-output signal. You do some simulation of filters. Basically, this could be also pre-computed. You don't really need to compute it once you have your data set. You filter the input-output data, and by the way, all this can be done offline on MATLAB, whatever tool you want. And once you have your simulated filters, you can sample the signals of these filters. And once you have these batches, you just plug them into an LMI, which produces a stabilizing gain. The resulting controller will be the interconnection of an observer for a non-minimal realization and a feedback gain with the states of the non-minimal realization. And this is the architecture that we have obtained. Note that, different from the model-based approaches, the dimension of the observer is non-minimal. And this is necessary, by the way, in order to obtain what we said, a simpler representation of the dynamics with a parameterization which is good enough to do everything without having any explicit knowledge of matrices A, B, and C. But now, considering that we have 10 minutes, I will go slightly quicker, but we are almost there, actually. In order to solve the output regulation problem, we are very close because if we look at the original output regulation problem, and we consider that in order to solve it, we need to embed some kind of feed-forward term depending on W, but we don't know W. The best and probably the most consolidated approach to solve this problem is to embed an internal model in the control architecture, which is based on this very well-known paper based on geometric theory, which says that in order to solve the output regulation problem, as we said, we need to embed into the feedback loop of the controller a copy of the model of the disturbance that is affecting the system, which is what is called in the literature as internal model unit. Of course, this is a property that holds for linear systems. The generalizations to nonlinear systems are much more complicated, but we're not focusing on them. So in practice, what has been done for decades for linear systems is basically this. So since we know S, we find similar as before, a simplified version, so a minimal representation of the modes of the exosystem. And using that, we define the so-called internal model unit, which is basically a parallel architecture which processes every channel of the regulated error here with the pair S0 gamma 0, which is a controllable pair with S0, which contains all the modes of the exosystem. So the classical result, since the times of Davison in his paper, is that if we consider the augmented plant, which includes the plant and the internal model unit, and if we find a stabilizer for this augmented plant, we have automatically found a solution to the output regulation problem. In other words, the real interconnection will be that from the plant we process the error and we obtain the states of the internal model. And using the outputs of the plant and the state of the internal model, the stabilizer will assign the input. So let's say, the philosophical reason why I presented this is that what we only need to do is to perform stabilization. We have transformed, using the internal model technique, a tracking and disturbance rejection problem into a stabilization one. And so we do exactly the same thing as before, just a little bit more complicated. So I will go very quickly here. Starting from a plant with perturbations, we can filter exactly as before with an observer and an internal model unit, the input and output data. We define an estimation error, and we obtain a cascade representation, which is more complicated, but conceptually the same as before. And we also see, using properties of based on the non-resonance condition, that this cascade here is stabilizable. And because of that, thanks to that result, we can do the same thing as before. So use a feedback gain depending not anymore just on z hat as before, but also on eta. And so the block scheme that is achieved is this one. So you have an internal model, you have an observer for the non-minimal coordinates, and both the states of these two guys here are used for a static feedback gain. And the only remaining part is to design an LMI to compute k, as before. So the algorithm is essentially the same. So you filter the data, you acquire a data batch, you solve an LMI, and you find a controller, a gain, k, which provides the control for the system. And that's it. So just to provide some final considerations, the interesting and challenging part of all this result is how to design the matrices for the non-minimal realization. So how do we do that? Well, it's just an intuition here, but if you look at what has been done for the internal model unit, it turns out that the same exact thing can be done for the observer. In particular, the structure here is given, like here, as a parallel interconnection of many filters. Now, these are not neutrally stable, but asymptotically stable. And these filter process each channel of the output and the input of the system. Of course, I'm omitting a lot of things which can be found in the preprint, but in particular, we need that the pair lambda f LF is controllable, and this matrix has different eigenvalues. And of course, the dimension of lambda f is not free. It needs to be sufficiently large in order to capture the complexity of the system. It turns out that the dimension here is related to the observability indices of the system. Anyway, for the SISO case at least, the dimension is equal to the order of the system. Just to provide some final remarks, note that the non-minimal observer has very striking similarities with other tools in the literature. First of all, the nonlinear Luenberger observer is exactly the same. The only thing is that it is used for a different purpose, in this case, to recover the state estimate. But notice that this is a filter with the same exact structure for only the output. And here instead we're using both the input and the output. But also the internal models in canonical parameterization that you can find in the literature are filters in the exact same form, processing the input instead of the output. So we are finding something that in some way should be connected. And it's an interesting topic for potential research on this. So here's just an example. I won't go over this because of the time constraints. Anyway, I think it's more interesting to discuss just a couple of potential future work on this. Well, first of all, a very important thing is how to deal with noise, of course. Can we also deal with like noisy data sets? So this is an open question, which can be addressed using tools like set membership approaches in the literature. And another interesting topic is how to address nonlinear systems. So these tools are fully in a state space setting. So they are somehow ready for work in the nonlinear context. There are already some potential connections, like with the Koopman theory, and potentially also with bilinear systems. So there is a lot to do in this context. Of course, for the purpose of the project that I introduced, a very important thing will be to go beyond continuous time systems. So to address also the control of hybrid dynamical systems, because it turns out that in many mechatronic applications, there are inherently hybrid systems. So I just arrived at the end of the hour, and I present to you also this link, which is a link to a GitHub page where you can find basically all the material for this presentation, and also some MATLAB code that you can run and test to see if it can be applied. And if you have any question, any consideration, just you can send me an email. Thank you very much for your attention.
Okay, thank you so much, Alessandro, for your very interesting talk. Is there any question from the audience?
Yeah, I have a question.
Yeah, sure.
I think I missed something. How you calculate z hat dot?
Yeah, that is in fact something which could appear to be a little bit strange, but if you look at let me just go to the stabilization algorithm. Of course, you may say, well, this shares the same potential drawbacks of the fact that an ODE holds almost everywhere. But when I mean that I computed the derivative, I mean that I sampled the right-hand side of this differential equation. So in every point that I implement this. So every value here is nothing else than f z hat of like tau s, gu of tau s plus ly of tau s. So this is how you implement it. So
Then F, G, and L should be
unknown.
no, right?
Exactly. Exactly.
Yeah, I missed this part. How you know this part?
Yeah, the thing is that in general, you need to design them in a suitable way. And it turns out this is something that is shared also with adaptive observer literature. If you choose F and GL as filters that you choose, it's you that chooses the form of these filters, but they are sufficiently big in some way. You don't need any information from the plant. So this is kind of a surprising, in some ways, striking result, but it it's the powerful thing that I mean, that appeared since the times of Kresselmeyer observer design.
Do you know FLG is